Okay, to start off, we have lists, and for a list, I like to use L1, but you can use any variable. And you just put brackets, and you separate each item in the list by a comma. And again, just to show you, like, any variable you can set to it. But L1, and then I have this list right here just to show you everything else. For stats, we have mean, sample standard deviation, population standard deviation, and if you do stats of L1, it'll show you all of this stuff from min, quartile 1, median, quartile 3, and max. You can see all that right here. If you want to get more specific with these, you have the median, min, max, and quartile functions. For the quartile function, you're going to do your list, comma, and then 0, 1, 2, 3, or 4, which just is the same as min through max and the stats function. To graph it, here we have a histogram. If you're not lined up, you can use this zoom fit button. Just puts it into perspective. It's very useful. And right now I have it set to the left bin, which is pretty common, like 10 to 11, 9 to 10. And then center will be like from 9.5 to 10.5, around the whole numbers. It doesn't matter too much in this case, just because our list is all whole numbers. Another useful thing you can do is go to relative. It gives you the proportion for each bin instead of just the count, which is what that one is. And you could also change the bin width, like your list, comma, bin width. You can see there. It's very useful too. The box plot is right here. You can change the offset and the height. I find it really useful if you're comparing histogram and box plots. Go back to 1. The bin width, you can kind of see putting it below, like an offset of like 3-ish. You can make it wider too. It's easier to see. That's a really good thing to do. Lastly, there is the dot plot. Right, that's in there. It's really weird. It's most useful in a bin width of 1, at least for whole numbers. But it gets really weird on Desmos. You have higher bin widths. And last we have normal distribution. I like to set variables to the mean and population standard deviation if you have a list. This means like A is effectively our mu and B is our sigma, lowercase sigma. And we can actually put that in as our mean and our population standard deviation to get this normal distribution. And this cumulative property is going to act as our CDF and inverse CDF functions. So you can see here it starts off with 1 standard deviation below and above, which is why I have 0.683. You can click on it for the more specific, but it's like our 68 rule. And what's useful about having these variables set to our mean and standard deviation is you can set the bounds as something like a minus b to a plus b. You get that, and you can go from 2b to 2b on both sides, 95%, 3, and you can see 99.7, that rule. And you can also do left, like x is less than, I don't know, if you want to do like a plus b, you can see that, right, and outer functions. And then you also have the bounds, so if you want to say like 70th percentile, and then what number represents that in the distribution. The other way to do this is if you do period CDF, and then you can do like a minus b to a plus b. It'll give you that same thing. It's also, and then if you want to do from the left to a number, to the right to a number, you could do negative infinity, that number, or you could do a minus b comma infinity. A minus b infinity, get that. If you do the inverse CDF function, so something like 0.75 again, it'll give you that number, the percentiles. And lastly, you can actually do a random function and set how many numbers you want in a list. So this is useful if you're just given, say, like, create a list, and this is your standard deviation, this is your mean, and you can just create a list with that and then find stuff. If you want to set this to L2, put your stats, L2. That's a really useful thing you could do.